Good morning, IB. How are you today? We hope you're enjoying calculus and enjoying having some fun differentiating things. What we've got up here is just a bit of a review, so you could pause the video and just spend a bit of time going through those. They are getting more tricky and more challenging. So see if you can have a go at those and then come to class and we can go through them on the board. But today what we want to do is have a look at the next section on the differentiation of logarithmic functions. So remember with our logs that we've got your basic definition of your logs is if you have some, I'm just going to use an n for some number, and that can be written as some base to a power. All right? So if we write that as a log, then we write log base, whatever our base is, of the number equals the power. So when you're taking a log of a number, you're finding out what power you need with that base to make the number. So we want to remember all our domain for these functions. So what sort of values can our number be? Obviously that can only be positive. We're only going to be taking a positive base so that we don't get our numbers flipping around. So our base is always going to be positive and not equal to 0. And our number is always going to be positive and not equal to 0 because there's no power that's going to make any positive number a 0, and if we have negative numbers it gets messed around. So remember, this is what our graph looks like. That reflects our domain. In this case our x is the number, so what number, so this is our x here, what number are we taking the log of, and what numbers can come out are the powers. So this, the y value is the power of the base, that's p there, and that can be any number, positives or negatives. Now let's think differentiation. If we think what's happening to the tangent, so if I could draw lots of little straight lines for the tangents here, really steep, not so steep, getting less steep, will we ever get 0? Does that ever reach a maximum? No. Will it ever be negative? No. So then that means if we want to do a graph, our input can only ever be from positive n values. So I'm going to make this a little bit shorter. Chop, 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 chop it off. All right, so come back to here, and our x-axis is n, the number, and our gradient starts very positive. There's an asymptote at n equal to 0, so nothing happens here. Very positive and gets less and less. Does it ever reach 0? No, but approaches it. So an asymptote at n equal to 0 and the y value. There's no x, so we won't have that. All right, so that graph hopefully looks familiar to you. It looks like our 1 on x, and in fact it is. So the derivative of this function is 1 over x. Note that this is only going to work for a natural log, not for a log base 10. So in this case we're always working with the log base e, ln of e, ln e, which is the base e. So let's now apply our chain rule. If we've got the natural log of some function, then if we differentiate that, remember our rule, we take 1 over, do the outside inside, so it'll be 1 over is the main outside function, and whatever our little function is going to be in the denominator here, times the differential of the inside function, f dash x. All right, so we could write that then as f dash x divided by f of x. So that's your chain rule. So let's have a practice at these ones. Oh, what else do I have down the bottom here? Is there anything else interesting down the bottom? Oh, an example. Oh, there's the answer. I won't look at that one yet. So, ln of 2x plus 3, that means we're going to go 1 over 2x plus 3 times the derivative of the inside part. All right, so that's our inside part. Derivative of that is just 2. So we've differentiated the outside part and come up with the inside part as well. So we end up with 2 over 2x plus 3. And I had that answer sitting down there waiting. So we've got that now. All right, so now let's look at some other examples. These ones are out of your book, but let's just go through them because they're nice. They cover a full range of ones. So in the first one here, differential of this one, dy dx. We've got a function inside a function. So here's our little inside function, and our outside function is a log. So we go 1 over the inside function, leave the inside function the same. Now multiplied by the derivative of the inside function is k. So we end up with k over kx, which is equal to 1 over x. This one here, same story, it's a bit like the one we just did. So dy dx equals 1 over the inside function, 1 minus 3x, times the derivative of the inside function, which in this case is minus 3. So we get minus 3 over 1 minus 3x. Can't simplify that anymore. Oh, right. This one here. Oh, this one looks a little different. Hopefully now you're going to start to recognize when you've got a function times another function. So here are two different functions. So the moment you see that, you're going to think product rule because they're being multiplied, or quotient rule if they're being divided. All right, so let's get to going with our product rule. Let's make our u and our v. So u equals x cubed. U dash is 3x squared. V is ln of x. V dash equals 1 over x. So remember our rule, dy dx, or y dash, equals, we want u dash v plus u v dash. And what's nice about the product rule, it doesn't particularly matter what order you multiply them and add them. Let's just stick with that pattern. So we want u dash times v, we want those two being multiplied, and then we want u times v dash. So we're going to have 3x squared ln of x plus u is x cubed times 1 over x, which is v dash. They cancel. These ones are going to cancel, so we can simplify. So always do this next step. You'll usually find you can do some little simplifying. Don't just leave it at that first stage. So x cubed times 1 over x makes x squared. Here we've just got a quick summary of our rules. So remember, with our logs, we've just talked about what's inside the log has to be positive, and in here it can be any real number. If you multiply two terms inside the log, that's the same as adding their logs. Dividing is the same as subtracting, and a power of n, the n can come down the front. So when we look at this example, there's another way we could have done this, is we could have rewritten our y equals ln of kx, where k is any sort of constant, the same as ln of k, because these are being multiplied, we can add the log of both of them. So we could write it like that, which means y dash or y prime ln of k. If we differentiate that, is that a function in x? No, there are no x's in it, so that means it's just a constant. So this here, in other words, it's just some number. That's a constant. Because k is a constant. We take the log of a number, we still just get a number. So that becomes 0 plus ln of x is 1 over x. So our y dash becomes just 1 over x. And it doesn't matter what that constant is. And that's what we saw in this example here, doing it a different method. All right, so here we're going to do two examples. This first one, we're thinking, right, there's a multiple applying inside, so we could do that chain rule and do the differential of the big function and the differential of the little function, but it makes it a lot easier when we split it at this point. So we can make that ln of x plus ln of e to the minus x. And if we keep doing our rules further, this is still ln of x plus minus x, that's a power. This power here, remember, can come down the front. Whether that's an e or not, it can still come down the front. So this is the same as minus x ln of e. And what's ln of e? Hopefully you've remembered. ln of e is the same, equals 1. So therefore, this is the same as, oh, we'll get rid of that plus, and we go minus 1. Now, oh, that's not dy dx. Sorry about that. We're just playing around, making y into a nicer way to differentiate. So now we know y can be written like that. So now y dy dx, we can now do our dy dx, is equal to 1 over x plus 0 because, oh no, oh, hold it, mistake. Did you spot that? That should still be minus x. I was thinking, what's happened here? Because that equals 1, so the differential of minus x becomes minus 1. I was jumping ahead with the differentiation before I got there. All right, so that's that first one. Remember, domain, a derivative function's only ever going to exist where you've got the domain at the most, where the domain is of the original function. So if we're thinking domain, then all of this inside here we know has to be greater than 0 because we can't take the log of a negative number. Is e to any power greater than 0? Always. It never goes below that x-axis. So as long as x is greater than 0, then that function works. This next one is a little bit more complicated. So here again we need to think domain. That's all got to be positive. If we're squaring a number, then that part will definitely be greater than 0 because any squared number is. But this part here is saying, remember we can't have that undefined, so that means x has to be, we need all of that greater than 0 and not equal to 0. So let me just, I need to make sure all of this denominator part, that bit now has to be greater than 0. So what does that look like as a quick sketch? It's a quadratic, concave up, x-intercepts at 3 and minus 2. So that's what that will look like. So what x values can we put in that will make the overall function positive, then we're going to see that this area out here, the function is positive, and this area, the function is positive. So if we pick x values that are less than -2 or greater than 3, then they get, any negative x's get squared up here, we'll end up with a positive number. So that means our domain is going to be x is less than -2. It cannot equal it, because then we'll have zeros and we don't want to divide by 0. And we have x is greater than 3. So do start to think about your domains with these. All right, so that looks really complicated. Let's do the simplifying, and we're going to go, remember, if we're dividing, we subtract. If we're multiplying, then we can add them. So let's start off with ln of x squared minus ln of x plus 2, x minus 3. Now let's split that further. So we're going to go, and let's bring the 2 down the front. For that, we're going to go minus ln of x plus 2 minus, because the minus belongs to both, ln of x minus 3. Don't forget to put those in brackets so we know the log belongs to them all. Now that looks so much simpler for factorizing, for differentiating. Imagine doing that. You'd have to do the big function, and then the inside would be a quotient rule and messy. But this, because of our log rules, is so much easier. So now we can differentiate. So the differential of ln of x is 1 over x, so we're going to have 2 over x, because of that coefficient 2, minus 1 over x plus 2, times the differential of inside, and that's 1, because the coefficient of x is 1, minus 1 over x minus 3, times 1 again, because the coefficient. So much simpler. If we want to put that as one term, then that's a bit of fun with your algebra. So as I said back here at the beginning, have a go with these initial questions and bring those to class. So thanks for listening, and hope you have a good day. Bye for now. Bye for now.